geotechnical engineering, they deliver lecture, and it is these lectures are very well attended, not only by the IGS Roorkee chapter students, but all over India. So I'm sure that whatever discussions are held in this particular lecture will be very beneficial to all of us, not only the students, but the faculty members also. Okay, so with these words, I again welcome you. Thank you.
Thank you, sir. Today we have our faculty coordinator, Professor Kaustav Chatterjee, also with us. So I request him to speak a few words before we start.
Yes, thank you, Pratik. So it gives me an immense pleasure and honor to have Professor Piyush Samui with us to deliver this lecture on basically the soft computing skills and its application in the domain of geotechnical engineering. And I also agree with Professor Samadhya, the head of the department. It is regarding the work that presently the student chapter is doing. We are organizing webinars, online lecture series, and more than that, it's also a pleasure that whenever we are having any expert who is coming as an examiner to examine the PhD scholars, we are also having a lecture on for that particular persons. So in this ways, the entire student community, particularly geotechnical research scholars, the MTechs, they are really indebted to gather good information, knowledge about the recent updates that's going on in various domains of geotechnical engineering. Okay. Thank you, Pratik.
Thank you, sir. We all know Professor Samui. Yeah, he has done a vast work in the field of AI, ML, and geotechnical engineering. But to formally start the event, I request Professor V.A. Sawant, sir, to introduce our speaker before he delivers his lecture.
I welcome you all.
Sir, you are, yeah.
First of all, I welcome you all for this webinar arranged by IGS Student Chapter Roorkee. It is my privilege to introduce expertise like Dr. Piyush Samui. He is professor in civil engineering at NIT PATNA, India. He completed his BTech from IIEST Shibpur in 2000 and done his master's and PhD from IISc Bangalore in earthquake geotechnical engineering in the years 2004 and 2008. He also held postdoctoral positions at two universities, first at University of Pittsburgh, USA, followed by Tampere University of Technology, Finland. With over 14 years of experience in the research, teaching, and consulting, his work encompasses geotechnical and earthquake engineering, materials, reliability analysis, site characterization, and AI applications in civil engineering. He has authored 5 books, over 225 journal publications, and numerous edited volumes. With an H index of 43 and more than 5,600 citations, he is widely recognized internationally. He serves on the editorial boards of several journals and contributes to professional committees, including the Indian Geotechnical Society and ISSMGE Technical Committee on Machine Learning and Big Data. His honors include the IIT Roorkee Shamsher Prakash Research Award, the IGS Sardar Resham Singh Memorial Award, and the ISCMAG Excellent Regional Contribution Award. He is a fellow of the Indian Society of Earthquake Technology, a guest professor at the University of Science and Technology, Beijing, and holds the title of docent of Tampere University. He is giving the lecture on 2 days in the area of advanced machine learning in geotechnical engineering. He is second to none in the geotechnical engineering in the fraternities in geotechnical engineering in India. With these few words, I request Professor Samui to deliver his lecture.
Okay. So good evening. So Professor Samadhya sir, Professor Kaustav and Dr. Sawant sir, and Pratik also. Thank you for the opportunity. Actually, IIT Roorkee is very special for me because first recognition what I have got from IIT Roorkee, because Shamsher Prakash Award I got in 2011. Before that, actually, I think many people doesn't know about me also. But it's a good recognition. So that is one thing I want to tell. So coming to today lectures, actually, I start with I think if you can share in the presentation. Can you see my screen?
Yes, yes.
Yes, sir.
Can you go to full screen mode, sir?
Yeah. Now
Yeah.
it's okay.
Yeah, fine, fine.
Yes, sir.
Yeah. Yeah. So I think title already everybody knows. So I'm directly come to the what I will discuss today. And so what is the concept of the hybrid email? Actually, if you look at that email, actually long back it has started in civil engineering field. And so traditional email, whatever is there, neural network and all these, that is a little bit saturated in the field of civil engineering. So for new research topic, we have to go some advanced level, and that is one is the concept of the hybrid machine learning model. First, I will discuss. Next is the large language model. Nowadays, we are talking too much about the large language model, how we can solve various civil engineering problem also. And then future application and some of the take home message, actually, that is general take home message. So if you come into the ML model, machine learning model, actually what we are doing with traditional machine learning model, we generally try to make the error should be close to zero. Actually, we want to minimize the error of a particular prediction. For example, if you have to predict the bearing capacity of the soil, so that your model should predict the bearing capacity of soil close to the actual value, what you are getting from the experiment. So that means you want to make the error should be equal to zero. So when you are making many things, you are making that minimizing one function. So you want that your should be error should be here. Actually, it should be zero. But actual case in traditional machine learning, if you apply, then it can go anywhere actually, because -1, -2 also it can go, because that is the minimum value. So, but we are not interested all this here also. But if you go actually by traditional approach, then we are unable to get the good result. So that's why if you tell, and we cannot control the traditional model also, that you give the always the minimum value should be zero. That is not possible in traditional optimization problem. But if you go by the hybrid machine learning model, you can tell the model that you go that I want that use the meta-heuristic optimization. That is one optimization technique. If you can apply this meta-heuristic optimization technique and with combine with the machine learning, then we will get the hybrid machine learning model. Now, coming back to the, I am not going to the details of what is the machine learning, actually what is machine learning, but I will go what is meta-heuristic optimization. A little bit introduction I want to give to get an idea that how we can apply for any geotechnical field. So there is one thing that no freelance theorem. Actually, one theorem is there. That means there is they told that it has been told that there is no universal algorithm for all problems. So if you see that, you cannot tell that you, for example, there is a various machine learning model is there, but you cannot apply, for example, liquefaction, bearing capacity problem, pile foundation problem. You cannot apply only one model. You cannot tell that engineers that you use that base model for the all problem. So that the problem arises. That means you have to check that which model will give you the best performance. That means there is no standard rule is that for any machine learning problem or machine learning model, that you use this model for this problem and it will give the better result. So every model you have to try, and you have to and for that you have to find out that which is the best model. So now choice of, when we are coming to the meta-heuristic optimization model, the choice of algorithm is very important. What is the one type of one? There is a two types of question is there here. For example, if you take a one type of problem, for example, if you take a soil bearing capacity problem or retaining wall problem, then what is the best algorithm to use? Actually, what is the best algorithm you can use for a particular problem? And second is that, for example, somebody is giving algorithm, it is constant for you, and what kind of problem you can solve it. You can what kind of problem you can solve it by using this algorithm. So coming back to the meta-heuristic optimization, actually, the term meta-heuristic was coined by the Glover in 1986. It is nature inspired. Nature inspired means what is happening in the nature, whatever the phenomena is happening, based on that, this model has been developed. And there is a random variables actually is there. For example, if you take as a soil bearing capacity problem, the random variables mean C, phi, gamma, and the width of the foundation, depth of the foundation, all these. And another thing is that there is one interesting things is the material optimized is there, that there is no require the substantial gradient information. That means you don't require the gradient information. That means if you see that if you want to traditional um, optimization technique, always you have to calculate that dy by dx. That means you have to derivative of the function you want to optimize, and that you have to make to zero. That means gradient is a main issue in the traditional optimization technique, but in materialistic optimization technique, that is not the issue actually. So there is a lot of advantages there if you apply the materialistic optimization technique in machine learning model. So what is the component of the materialistic algorithm? Actually, it's a exploitation and exploration. So exploitation means you take that one local region. For example, you have taken one problem and you are trying for the various variables. So you define that your C is from this range to your C minimum maximum range. Gamma is the minimum maximum range you are giving. And your phi also you are giving the minimum to maximum range. And for the local region, you search and you find out that what is the good solution for that region. For a particular region, what is the good solution? And exploration means to generate diverse solution, so as to explore search space on a global scale. That means you will do overall search in the global scale and to get to the explore it. So there are various methodistic optimization algorithm is there, and every day you are getting a new algorithm. So various is the evolution algorithm, human-based algorithm, the swarm intelligence algorithm, and physics-based algorithm. So plenty of algorithm is there. But the now question is that which one you will use for a particular problem? That is a very difficult question to answer, and that is a very tedious job for a civil engineering people. Is that the particular model which one you will use? So I will give one sample application that how this materialistic optimization problem can apply. So we are taking one problem of the estimation of the soil compression index of a particular place. We have taken the data set of that point, and the soil compression index actually calculated based on the various index properties. That is, so data has been taken from the work of this one railway project is going on in this place in the Gujarat. So there are around 700 audiometer test result was acquired from this. That is actually L&T has given the data set to us. And there we are getting the various properties of the soil. So various properties means the gain size analysis, all these properties, and compression index also. So what are the properties we have got actually here? We have got the depth of the soil sample, specific gravity, bar density, dye density, gravel content, sand content, silt content, clay content, liquid limit, plasticity index, and free soil index. So these all parameters we have got. So around 695 data set we have got from this company. And so these parameters all we will use as an input of the model, and the model will give the compression index. That is the CC value. And so this is actually I have done that one of the statistical analysis. That is very simple things you can do in the Excel or MATLAB also. So all data we have calculated the minimum value, average value, maximum value, standard error, and the standard deviation, kurtosis, and the Q-ness. So this all parameter we have calculated for the various parameters, and to get an idea that how our model is heading actually, what is the range of the data is there. So here actually one thing I have done, if you see that we have data set actually many parameters are there. So it's a multi variable parameter is there. So whether we can reduce some of the parameter that is not useful. So what we have done some principal component analysis. So generally it is used to reduce the number of variables of the data set. For example, some of the data set will not use for prediction of the some parameter, for prediction of the output. So we will determine based on the principal component analysis, and principal components are the principal component analysis. Actually, it itself is a one subject. You have to put one lectures actually. So I'm not going to the details about the principal component analysis, but if you do the principal component analysis, based on that you remove some of the data set from your data set. So that is not very useful. So here actually principal component analysis we have done, and if you look at, there is, we have get some parameter actually, and what is the principal component parameter is also there. If you look at that, how the parameter value percentage of the explanation has been reduced of the principal component. So around 12 data we have used. So based on that, we have removed some of the values from our data set. Now coming to the how to use the hybrid AI model, what is the steps? So you actually, we have the main data set and the dimension reduction has been done. So we have not taken all parameters. Based on the principal component analysis, we have reduced some of the parameter. And we have normalized the data set between 0 and 1. So we have normalized as the data set, whole data set into 0 to 1, because normalization is very important to keep the all data within the range. And then we have divided the data set into two parts. One is the training and the testing part. So training actually we are doing by various model. So one is the neural network based various optimization technique model. Another is the extreme learning machine. That is another technique. There is two models, two traditional models is there. One is the artificial neural network, that is ANN, and another is the extreme learning based model. And that is various optimization problem, equilibrium optimization problem, particle sum optimization problem, all these. And I have used some of the traditional AI model also, random forest, gradient boosting machine, and genetic programming. So these all model we have used to determine the compression index based on various parameters. So how the result will come, so how the result actually. So when you are making, when your prediction, when your model you are developed, then you use various parameters to examine that which model has the best performance. So we have calculated various parameters actually, that is the adjusted coefficient of determination, Wilmot's index of agreement, NAC, mean absolute error, mean absolute percentage error, RMEC, weighted mean absolute percentage error. So there are many other parameters also there in the, if you read any statistics book, but I have used for my model all these parameters. So this parameter actually, every parameter has some ideal value. For if you use any good model, so you have to for a good model, if your model parameter values, if it's very close to one parameter, then your model is good. So this is the ideal value actually. I have given all these things. So if you look at that, there is various ideal value of the various parameters. So if your model, if you calculate the parameter, and if your model is, if your value is very close to this model, then you can tell your model is the best model. So now actually, what is the design parameter? So there is a various design parameter is there actually in ML model. So this has been done during the training of the model. So this is the extreme learning machine. This is the extreme learning machine of the various meta-heuristic optimization technique. So this is the number of hidden neuron, number of hidden layer, population size, the maximum number of iteration, inertia weights, acceleration coefficient. This is all parameters has actually various for the various optimization technique. So all optimization technique, that is actually very tedious job. Just like in traditional optimization technique, one advantage is that everything is the mathematics. That means you calculate the dy dx, you make that 0, and then you put the value, then you will get the minimum value. But here actually you have to tune the parameter, you have to tune your model so to get the best solution. So to get the best solution, so that is such a very, very tedious job when you are developing any machine learning algorithm. So there are various parameters there, and that design value, this parameter has been developed during the training of the model. So this is the convergence curve. If you look at that, how the number of iteration we have used, how the RMEC value is reduced as the time progress. So as the time progress, automatically your value is decreasing. Similar trend has been observed also in ANN model also, as well as ALM model also. So this is actually, if you look at, so one thing you look at that we are not getting the value actually close to 0, almost 0, but not 0. Actually, generally, you cannot tell any model in machine learning, you cannot tell that you cannot force any model that you should give always a 0 value. Because in actual traditional, if you look at, if you apply your common sense that in this world, actually, there is no model is there which can give you the perfect result. For example, you are doing some experiment, and if you try to develop a model and your model will give the perfect result for all data sets, that is not possible. So always we will not force the model in a machine learning model that it should be close to zero. That means you are overtrained the model, you are overfitting. That means you are forcing the model that you should be give the better result. So that is the performance index of the training data set. So if you look at that, there is a various parameter actually calculated. If you look at that, so ELM MEO actually give the best performance than all other model. So that means ELM MEO is the best better model for the all other model for the training data set. So this is for the training model. So during the train, we have observed this one. Now for the test data set, if you look at here also ELM MEO is give the better result. That means you can in this you can tell that so this model is the best model for prediction of the compressor index. So now this is one of the quantify that based on the parameters. So now I have to discuss some of the scatter plot also that how if you plot the data set, graphical visualization of the data set. So we have plotted the actual data in the x-axis and the predicted data in the y-axis. So this is actually actual is equal to predicted line. So you see that there is a various training data set, all plots are there. So you can look, you can see that for almost every model has given reasonably quite good result, because if this line is the actual is equal to predicted line, and your data set is close to this line. So cadence plot was a testing data set. If you look at that is actually actual value in the x-axis and predicted value in the y-axis, and the data set this is not in the data set is very close to this line also. That means here actual is equal to predicted line also. And if the data set is very close to the line, that means your model is quite good. So this is actually one of the graphical representation. You cannot quantify, that is, you cannot qualitative analysis is not possible. So Taylor diagram has been also developed actually. One of the that is very interesting diagram actually. If you look at that here, actually we are putting the standard deviation of the data set, and this is the standard deviation, another standard deviation, and this circular line is the your root mean square error line. That means, so it is coming from zero, it is starting from the zero here. So you know that mean square error for a good model should be close to zero. That means if your point actually lies here close to this line, that means your model is good. As your data set is quite far from this point, then your model is not good. And this radial line is actually coefficient of correlation line, and that is R is equal to 1. So if this is R is equal to 0.9, 0.8, so that means as you go from this point to the far, then your model will be not good. So if it is close to this line, that means you can tell that model is good. So this is the one graphical representation of a particular performance of the model. And but one thing is that you can buy this model, you can two parameters we can check. One is the correlation, another is the mean square error. So this is the error matrix has been developed of the various model, as actually where the red marks is the maximum error is there, and as the from the red maximum, and as the red from the green, it is green means minimum value for the training and testing data set. You can easily develop in the by Excel sheet. So next topic, actually very interesting, is that a large language model. Actually, everybody is talking nowadays. So what actually large language model? So if you've seen that in the previous things, data set we are giving as a values. For example, we are giving the value as a C, phi, gamma. We are that C is equal to 20 kPa, phi is equal to 15 degree, and gamma is equal to 18 kilonewton per meter cube. That all data we are giving as a value. That means you are giving the model as a all values. You are not telling that the soil C value of the soil is 20 kPa, angle of phi of the value is 15 degree, and gamma is the value is the 18 kilonewton per meter cube. But in LLM, you can do this thing. That means you can tell the computer, you can tell the algorithm that I am giving that for example, I am giving, if you take a foundation problem, the depth of the foundation is 2 meter, width of the foundation is 1.5 meter, and my C is my cohesion of the soil is the 20 kPa, angle of internal friction is the 20 degree, and gamma is the 18 kilonewton per meter cube. then what will be the bearing capacity? So these whole things you can give to the model, and model will give you that, just like an output, that the bearing capacity of your foundation is uh, 20 kilonewton per meter square or 50 kilonewton per meter square. That means here actually computer can judge your model, your data set, that what type of data is coming before data is coming. Before that, they cannot differentiate between the C, phi, gamma, or width of the foundation or depth of the foundation. So plenty of application is coming now in large language model. Actually, it is basically a neural network and designed to understand and generate human-like text. That means whatever you are using, for example, you want to calculate the factor safety of a retaining wall in sliding case. Then you will tell that computer that height of the retaining wall is this one, width of the retaining wall is this one, C, phi, gamma is all this value you will give as a value of the C is this one. Then your model will give the factor safety or factor safety against the sliding. So what is the LLM is doing? So for example, if you take a particular slope stability problem, so if you see that you giving the model 20.3, 10, 35, 40, 4.7, 0.25. Now, if you show any these things, any any person who does not know anything about the soil mechanics, or if you show anything anybody, then he does not understand that what does it mean actually. What is 20.3? What is 35? What is 40? But in LLM, actually, you can give that my unit weight is 20.3, cohesion is 10, internal friction is 35, slope angle is 40, and slope height is 4.7 meter, and pore water pressure is 0.25. So that means this thing you will give the input. So what is there? So some layman who does not know anything about your software or anything, he can understand that algorithm also. That means he can get the output. So that is the main advantage of the LLM model. So I will give you one sample application that to determine on the slope stability problem. So I have taken the dataset of the on the Lean et al. In 2000 on published paper. So there is a plenty of dataset is there. Around 600 dataset is there of the particular slope, various slope. So this is actually your gamma value, and this is C, and this is phi, this is slope angle, and this is the height, and this is the pore water pressure coefficient, and this is status. Status means whether slope is failure or stable. That means it's a binary output, whether slope is failure or the stable, and this is the various location. So when you are giving actually your this text as a input, then it is calculated the text embedding a vector actually, and then so when you are giving the text actually, they are converting the text one vector, and then that computer is reading that vector actually. So what is the LLM architecture? If you see that, so generally it contains the transformer block actually. There is four things used there. One is the layer normalization, another is the GLU activation, that means activation function we have used, and then feed forward network and shortcut connection. So these are all parameters actually. These four blocks, four steps are there for developing the LLM architecture. And we have divided the data set into training data set, testing data set, and validation. So we have taken a three part of the data set. So training is around 268, 78 is testing, and validation is 39. So now we will try to develop the model. So this is the layer normalization. If you look at, so here actually this is the layer input you are giving, and you are getting the output through the network And after layer normalization we are doing here, after layer normalization, so we want to make the layer normalization means that if you take the data set, it will be the mean value will be 0 and your variance will be 1. That means your mean value will be 0 and the variance will be 1. So that means you want to normalize between 0 mean and the variance should be 1. So this is the layer normalization is very important when you are developing the large language model. So this is actually your that overall model actually. So you are giving the input actually, and then you are giving the tokenized text and token embedding layer, and then your layer normalization you are doing here. And there you are shortcutting and transformer you are using. That means you want to transform your data set into the text. And then you do the feed forward and all these things. So here actually one thing is that in traditional AI model, you require very less CPU. But here, actually, when you train the model, it will require the GPU and you require very high performance computing. Otherwise, you cannot develop the large language model because it requires more RAMs and more pace of the computer. Because it's a high deep learning model, you use plenty of data set. For example, you see that previously only 20 kPa if you give, that means it is soil C value. But now you will give that the value of the coefficient is 20 kPa. So automatically the computational cost will be very huge. So this is the training of the LLM model. If you look at, this is the training, how the epochs has been changed with the loss function. So you see that how the loss function is, epochs has been changed and loss function. This is the training loss and the validation loss. So generally we have stopped, if you look at that, as that epochs increasing, that there's a gap is increasing between these two. So where this gap is very less, that means around 45 epochs, we have stopped the model to that is the best model because at that time the loss is a minimum also. So based after that, we will try to develop confusion matrix. So this is actually, there is a very interesting thing is one of the matrix is there. So this is the actual level. Actual means negative. Actually, negative means when the slope is fail. That is, we are telling the negative. And your actual case is the positive, and actual case is the positive. That means slope is stable. And this is the in the y-axis is the predicted level. So when actual case is the positive and your model is predicted negative, that means around 7 cases there. And the negative actual case is negative, and a predicted level also negative. That is 123 case also there. That means that is also called true positive and true negative. True positive means when your model is giving actual result is positive and your actual result is also positive. That is called the true positive. And false positive means when your model is giving negative, but your actual result is positive. Similarly, true negative as well as true false positive also. So there are various parameters you can calculate actually. That is the true positive and true negative, and divided by the true positive plus true negative plus false positive plus false negative. So accuracy should be close to the 100. It should be close to 1 actually. And this is the precision and the recalls and F1 score. So this is all parameters actually to get an idea that how my model is performing. For example, if you're stable, for example, if you see that one interesting thing is that, for example, your stable, your slope is fail case, but your model is prediction is stable. That is dangerous actually, because that is not good actually. But if in case, for example, your slope is actual case is slope is failed, but your model is very stable, it is more dangerous, because that means it should not happen actually. That will be that's why there is a we are taking precision and recall and F1 score. So based on that, we can get an idea about the model capability. There are various parameters I have calculated to get the performance of the LLM. But one thing I have not done here, I have not comparative study. I have not done with other model of the traditional AI approach. So now, what is the future application? So I have shown two application actually. One is the prediction of the compression index. Another is the large language model for the slope stability problem. So what we can apply the future application? So one thing is that I think this is not also geotechnical, but I can tell you can apply the geotechnical also structural health monitoring. So this is very important. For example, if you have a foundation you have made maybe 20 years back, but the foundation today will not same condition. Maybe soil strength will be reduction will be there. Same, many things can happen. That is called the structural health monitoring. So in the structural health monitoring also, in the structural people, for example, structural engineering people are very much using the AI model, machine learning model in the structural health monitoring. But geotechnical people also you can use if we can get the data set from the soil and existing condition of the foundation. So present application, if you see that, so damage identification of the structural monitoring, earthquake engineering, structural damage identification, more, this is all for the structural analysis part. But same thing can be used, you can apply for your geotechnical point of view. Still, actually here, one thing we can do many things of the structural monitoring for the geotechnical point of view. Next is the monitoring of the infrastructure. That is, for example, there are many bridges are there in India, all over the India, that is very old, 50 years, 60 years. So what is the present condition of the bridge? So if you take the data set of the various data set of the pH, ions, all this moisture content, corrosion rate, all these of the bridges. So you take the data transmitted and you try to develop an AI model, machine learning model, and then you can condition, you can assessment. So you can assessment the condition. What is the condition of the bridges? So then you can tell that if it is very bad condition, whether we require the um, some management, infrastructure management or retrofitting of the structure. So aging management we can tell, and then we can do the service life prediction also do. So up to what the bridge will be okay, and the condition assessment also we can do. That means that condition assessment also we can do. But this concept I have taken from the published paper of a. So if you can read this paper, you can get an idea about that, how we can use the ML model for solving a monitoring infrastructure also. Next is the generative AI, actually very useful nowadays. Actually, here you can give the data set to a particular model. For example, you have collected one pile load test data all over the India. So from that, actually, if you give the model, so model will also give similar type of data set. For example, if you can, this is the pile depth, and this is the diameter of the pile, and this is the soil profile. So pile capacity, pile load capacity is coming by the pile load test is this one. So based on that, you try to develop the generative AI model, and then that if you apply the generative AI model, for example, if you have developed on pile foundation, you have posted on pile foundation, you give the data set, and then based on that model, you can tell that what type of capacity will be there. So, here in this generative AI can give a good prediction of the future things also. So it can be very useful for the geotechnical point of view. And next is the big data concept, actually very useful nowadays, because if you look at that till today, actually, if you collect the all over the SPD data, for example, all over the world, and all over the SPD data set, all over the world. So every day we will get the different data set, because every day there is some SPD going on. So if you collect the data set, that will be huge amount of data set. That means high volume, high veracity, high value, high velocity, and high variety. Velocity means how frequency you can, how frequency your data is coming. So this data set will be very huge data set, and that AI model cannot handle this data set. So you have to use, in this case, big data concept. Recently, one paper has been published by the Cortez et al. In Computer Science. Not even recently, I think it is almost 7 years back. So they are predicting the magnitude of the earthquake by using the big data concept, prediction of the earthquake, and a prediction that they have done. So if you read the paper, then you can get an idea that how the big data concept has been used to predict the what can be the prediction of a particular earthquake of the magnitude. So I am almost finishing my lecture. Some of the take-home message what I want to give is that one is that that AI is very data specific model, that is very general actually, because I have already told that you have to this is very data specific model. That means you cannot tell this is a model, this is the best model. For example, I cannot tell random forest is the best model you use for all geotechnical problem. No. So you have to check that which model give you the better result, and the result AI should be analyzed thoroughly, and decision to be taken based on the practical experience. That means you have to use the practical experience also sometimes, because you cannot believe the AI 100%. But one thing is that AI model can reduce the cost of project, because if you look at generative AI, if you can develop, for example, so you, for example, your SPT or SPD data set, generally 1.5 point interval, you will get the SPD value. But if you apply the generative AI, we can get some data set between 1.5. So that's why it can reduce the number of tests also. So if we reduce the number of tests, automatically the cost of the project will reduce. So that's all. This is some of the published books. This is all our edited book. So this book actually I have edited long back. I've got the invitation from the Elsevier to edit one book on neural computation. And this is my Amazon author profile. So, and thank you. Thanks a lot. And if you have any question, you can mail me or you can contact me also. I'm ready to help anyone. Thank you.
Thank you, sir, for the lecture. Wonderful lecture. Can we take a few questions?
Yeah, I think a lot of question is there in the chat box.
There is two questions, so I will spell it. First
Yeah.
question is from Ratmale Siali. Have we performed k-fold cross-validation on the dataset? If yes, what is its significance in validating the model's performance? If not, please explain the reason for not applying k-fold cross-validation.
Yeah, that's very good question actually. See, K4 configuration generally, I will suggest you use. But one thing is that K4 validation, one thing is that when there is a overtraining is there, then only you can use the K4 cross validation. But if your data set is not overtrained, that means your model performance for training and testing both are same. That is, there is no need for the use the K4 cross validation. But I will suggest you when you develop any model, no, you go for K4 cross validation. But it will be a little bit computationally, it will be a little bit demanding as well as it will take more time. But now you will create a lot of high performance computer is there. But one thing I want to tell you that this almost, I think I have done 5 years back, actually, this past work. So things are changing very fast. So I will suggest you, in your problem, you go for the K-fold cross validation. And I will suggest you go for the K-fold cross validation. But if there is a not overtraining, no, there is, I think there is no need for the, go for the K-fold cross validation.
Thank you, sir. I hope the query is solved. The second question is from Ms. Sonam. The question is, the LLM model is more preferable to classification problem, or it gives same accuracy for regression problem or to predict continuous variables?
Okay, that is a very good question you have asked. See, one thing I think if you can tell actually, if you look at actually, for example, we are taking one problem, the regression as well as classification. Regression problem means you take the soil bearing capacity problem or pile capacity problem, or classification means liquefaction, whether liquefaction will occur or not, or slope stability will be occur or not. So here, classification problem always very easy because it is a two output is there, and whether yes or no. But regression problem, there is a plenty of output is possible because you are estimating some values. So I will tell you that large language model, whatever you are telling that whether it is suitable for the regression or classification, it is suitable for the both model. That it depends on how your data set is there and how you are trained the modeling. That is very important when you are developing any AI model, how you are training the model and how your data set is there. If your data set is good, there is a no noisy data set is there, then obviously LLM will also give the good result.
Thank you, sir. We can take the last question. It is from Arohi. Hello, sir. I used to automate ASHA to determine the ground response analysis, so it gives good result compared to LLM. Or I should also try LLM.
Can you just repeat the question?
Hello, sir. I used an automated ASHA to determine the ground response analysis to its and so it gives good result compared to LLM. Or I should also try LLM.
Acha, I used an automated SHA determine. See, LLM actually one thing is that LLM one advantage is that LLM will give the text-based input you can give it. So you can try the LLM actually. If you have time, you can try that. This is the new things you can try. And you can check the performance whether it will give. But if you got a good result already, automated ASH, then you don't need to go for the LLM. Okay, that is very
Thank you,
simple
sir.
thing. Get a good result by using some model, then you no need to go to the advanced model. It is not required.
Thank you, sir. The last question we can take. It is from Dinesh. Can you tell me about hybrid models?
I think already I have told actually. So hybrid model actually one thing is that already I've told. I'm telling again. Actually, the hybrid model name, I think I am also giving or somebody also giving, but it's a hybrid means traditional optimization technique is there that we are not using. We are using some materialistic optimization. That means we are telling the model materialistic optimization and that this is my base solution. What is my base solution? My base solution is that my error should be close to 0. So, but in traditional optimization technique, if you look at, you cannot tell that. You cannot tell that my optimization, my minimum value should be 0. It is not possible. At materialistic, you can do it. But one problem is the materialistic will face. It's a heuristic. That means if this is you cannot tell this is a best solution. Somebody tell also I am got this result actually. Maybe you are getting more, close to that result. But in traditional model, your solution is not heuristic. It is mathematics. That means if somebody told that this is global minimum, this is my minimum value, it is minimum value. If you do, I do, anybody do, you will get a minimum value, same value.
Thank you, sir. I think all the question has been answered. So now, as we come toward the end of the session, I would like, on behalf of Indian Geotechnical Society Student Chapter, I, Sushant Rahul, the President, would like to thank you, the speaker, Professor Piyush Samui, for giving his valuable time for this lecture. I am very much thankful to speaker for sharing his experience on the application of soft computing in the field of geotechnical engineering, especially in the field of slope stability, which is very much one was the most common phenomena landslide we face in our state Uttarakhand. I am sure this lecture is very much beneficial for our audience who is working in this field. I would like to thank the Professor Samadhyar, HOD, Civil Engineering Department, Professor V.S. Sawant, Chairperson, IGS Roorkee Chapter, Professor Kaustav Chatterjee, Faculty Coordinator, IGS Student Chapter Roorkee, for giving his constant support for such lectures. At last but not least, I'd like to thank our audience for this lecture. Thank you, sir. At the end, I would like to request all the participants to open your camera so that we can have a group photo. Everyone, please open your camera. Thank you.
How many parties?
We have, sir, around 80 participants today.
Oh, good. It's quite a good number. Anyway, you can contact me through mail or phone also. I'm easy to help anybody who wants to work on AI in geotechnical or any other field also.
Sure, sir. Once again, sir, thank you, sir, for this lecture, for giving us valuable time, and thank you to all audience.
Thank you for giving me the
Thank you.
opportunity. Okay, thank you,
Thank you,
sir.
Thank you, sir. Thank you.
Stop and
Thank you, sir.